Hello everyone and welcome. With our first topic together, I'd like us to be introduced a little bit on the topic of what structures are. I want to thank you so much for being here. You could have been anywhere else and spent your time doing whatever else you wanted and felt like, and you're here viewing this video. I appreciate your time, so let's get right to it. Terrific. So let's dive right into this. What are structures? Well, I'm going to give you a very simple definition for this. And I don't mean that it's simple because you wouldn't understand otherwise, but simple because I don't want to get into very complex and technical engineering lingo. Okay? So let me give you this definition that works really well for me. The way that I view structures are as the bones and the muscles and tendons of a building. They are basically what give buildings their shape, and what gives buildings the ability to maintain their shape and their strength to keep their occupants safe. So I like this analogy because it reminds you basically how it works in the human body, and that's how it works also in buildings. They are basically there to keep your building up and straight, right? To keep it safe and strong for the occupants. Now, understanding how forces go through the structure of a building can be fairly complex and sometimes complicated. But I submit that actually understanding how the structure behaves doesn't necessarily have to be complicated. Okay? I'll give you an example. Let's look at this bridge. This is the fourth rail bridge in Scotland. It was built in the late 1800s, and it's a relatively complex structure. However, in terms of how the structure behaves, that can be relatively simple to understand. In fact, the original designers, the original engineers of this bridge published this photo as a postcard to illustrate how their bridge structure behaves. Okay? So that's what I'm getting at. For the purposes of our course together, we're not going to go into very complicated and complex techniques of how to figure out the forces in a structure and how to distribute them and design structures. Instead, we'll try to relegate our understanding to how structures work. We'll come up with some rules of thumb for sizing structural elements, and hopefully you'll leave this course with an understanding of structures so that you may have a meaningful conversation with other people in the building construction aspect related to structures. Which brings us, I guess, then to the discussion of the figure of the structural engineer. And I don't necessarily mean that single human that you would think as the structural engineer. I'm referring to that entity that is in charge of the structure of a building. Okay? And I want to give you what my definition of structural engineer is. It is, in my opinion, or the way that I view it, as that person or group of people responsible for making sure that the bones and muscles and tendons of a building are properly designed, are properly built, are properly located where they're supposed to be, and they are also safe for use and occupancy. And this must be true at all stages of a building's life. So that means before that building is built, during the construction of that building, and after its construction. Okay, so this sounds like a tall order, and that's where structural design comes into play, because you have to design the structure to work before it's built, during its construction, and after. We'll touch a little bit on structural design in a few moments, but before that, I want to talk a little bit about how structural engineers are regulated in Canada. We'll start with Ontario, okay? Because Canada is a confederation, each province is in charge of regulating the profession of structural engineers, of professional engineers in that province or territory. Okay? A structural engineer needs to be licensed in the province or territory that they work in, that they practice in. In Ontario, that body is the Professional Engineers of Ontario, or PEO for short. They'll issue then a stamp like the one that you see on your screen to every licensed engineer, professional engineer, so that they may seal drawings with that stamp. It's basically a way for somebody to look at the drawings and say, this has been reviewed and approved by an engineer. In every province and territory, the bodies regulating engineers, structural engineers for that matter, professional engineers, is self-regulating. That is, they make up their own rules, which all professional engineers in that province and territory must follow. In addition to that, also, engineers, professional engineers, and as we're talking structural engineers, must abide by the rules of the province. In Ontario, the rules of the province that govern construction are for the most part codified in the Ontario Building Code, the latest edition of the Ontario Building Code. And not because the building code is law, but because the law in Ontario says that you must use the building code. I know the difference is slight, but for all intents and purposes, the building code governs how building construction must happen. Okay? Now, getting a bit deeper into some of the important aspects for us related to structural engineering and the building code, I would direct you to Division C of the building code under 1.2.1.2, which describes a little bit what the design, what architects and professional engineers need to be designing according to the building code. There are certain things that an architect must do, and there are certain things that a professional engineer must do, and there are certain things that they both do. Which then leads me also to recommend for you to review under Division C of the Ontario Building Code 1.2.2.1, which lists very clearly all those specific items related to building construction that must be reviewed by an architect or by a professional engineer, or may be reviewed by both. Specifically, you'll find that very well cataloged and listed under Table 1.2.2.1. I recommend you go check these out and be able to find them. There's nothing better as I can think of than putting a test question related to, say, being able to find some information in Table 1.2.2.1 under Division C about whether or not a certain item must be reviewed by an architect or a professional engineer, or if it may be reviewed by both. Very well. Within Division B of the Ontario Building Code, Part 4 is the part that's, for the most part, pretty near and dear to all structural engineers. It is in fact labeled, the whole of Part 4, it's labeled as structural design. Within here, I would direct you to 4.1.1.3, which contains the design requirements. Basically, a list of items that must be designed specifically by professional engineers related to a building structure. Under 4.1.1.4, you'll also find the design basis upon which all structural engineers must do their work related to structures. I recommend you check these out too and are familiar with them. Okay? Now, I want to talk now a little bit about structural design, this process. And as you can see by this beautiful image that's just appeared on your screen, it's giving you a hint of what structural design is like. I'll give you my personal definition that does not contain too much jargon. Okay? I view structural design as that repetitive process where the structural engineer, whether the single human or the team of humans, repeat this process of first selecting the material of which the structure must be made of, and then locating the bones, the muscles, and the tendons of a building, and then sizing those bones and muscles and tendons of that building so that once they're in place and assembled, the building is strong and safe. That's my definition, okay? Not too much jargon. Now, if I use a bit of engineering jargon, because you'll hear this used in our business, it would be rewritten as this. The structural design is that repetitive process where you design the structural elements so that the building will not reach its ultimate limit states and will not reach its serviceability limit states. And this is also shown for you under Part 4 of Division B of the Building Code under 4.1.3. Go check it out. Now, ultimate limit states, serviceability limit states, what is that? Let me try to explain that to you, because that's some very fancy words to explain some topics that hopefully will make sense in a few moments. Let's start with ultimate limit states. And again, this here is used in Part 4 of the Building Code Division B under 4.1.3. Ultimate limit states is the fancy engineering way of talking about the strength of a structure and therefore the strength of the building. If you want to avoid ultimate limit states from happening, you want to avoid that the building, that the structure you're creating is not strong enough. You want to make sure that your structure is strong enough to support whatever forces are applied to it. So you want to avoid that the ultimate limit states happens, that is, that your structure is not strong enough. Okay? Serviceability limit states, what does that mean? Well, serviceability limit states does not refer to the strength of your structure. It refers to the feeling of safety that your structure has as it relates to its appearance and deflection. And by deflection, I mean how much it moves. So let me give you a bit more detail. A building must not only be strong enough, it must also make occupants feel safe. If you're in a building and the building sways too much and moves too much, or it moves every time a car drives by, the people occupying that building will not feel safe. It doesn't matter that the structure is strong enough, they won't want to use that building. So your building needs to be stiff enough so that it doesn't move very much. Okay? In addition to, your building cannot deflect too much, even if it doesn't move quickly, as to then make stuff like drywall crack. Right? If you see cracked drywall or cracked masonry everywhere in a building, you start wondering, uh-oh, is there a problem with this building? Why is the drywall on the ceiling cracking? Even though the structure is perfectly fine, if it moves too much, it will start cracking the skin you put on it, right? And that makes people feel unsafe. So even though the structure is perfectly strong, if it makes people feel unsafe, that's not good enough. So the two limit states that need to be avoided are the ultimate limit states, that is, your structure is not strong enough, and serviceability limit states, which means your structure moves too much. You want to avoid that from happening. That's what the building code says. Now, there is more. Okay? There's one further limit states in the building code that I want to share with you, which I like to call economy. You won't find this in any rule books or in the law. And it relates to basically the efficient use of material and labor. But what it really means is this. If your structure costs too much to build and to maintain, it doesn't matter that it satisfies ultimate limit states and serviceability limit states, it will never be built. So this is a third limit states I want you to keep in mind. Okay? Not only must your structure be strong enough, not only must it be stiff enough, it also must be affordable. I'm not saying cheap, but it must be affordable. If nobody can afford to build that structure, it won't be built. Okay? Alright. So, basically, if you want to make sure that a structure is strong enough, we have to understand the forces that are being applied to a structure, to a building. In engineering, in our business, we refer to these forces also as loads. So I'm going to list some of these loads for you so that we get to understand the terminology and what they refer to. These are also listed in the building code under Part 4. Let's start with dead loads. Dead loads refer to the permanent loads, the permanent forces which are associated with the weight of the structure. and everything that is fastened to the structure. So it can relate to, say, partitions. It can relate to floor, wall, ceiling coverings. That's interior and exterior coverings. And unlike all the other loads we're going to look at, dead loads can be quantified very, very accurately, because the structural engineer as the designer, the architect as the designers are specifically dictating what the structure must be made out of, the sizes of those elements, and how they must be covered with the skin that you put on it, right? The building envelope. Okay, so permanent load on a structure. Okay, dead loads, easily quantifiable and very, very accurately quantifiable. Live loads. These are outlined for you in tables 4.1.5.3 under Division B Part 4 of the Building Code. Check out that table. It relates to the variable load that you see in buildings that are associated with the use and occupancy of that building. So that includes people, right? You and me. It also includes the expected use of that building. So that's the furniture, the equipment, anything else you plan on storing in there. Say if it's like a library, books then would be a live load. Unlike dead loads, live loads are variable because they move, not just in time, right, different times of the day, they also can move geographically in the building. They're not very easy to accurately define and quantify, but that's what live loads, occupancies. Check out table 4.1.5.3 in part 4 of the building code, because that too would make a great question on a test, right, to find live loads associated with certain occupancies. Okay, now let's move on to those loads, those forces that are caused by nature on a building. The first one, we're very familiar with this in Canada, snow loads. Snow loads are again variable loads which include the weight of snow, the weight of ice, the weight of rain, or just rain, or all of them together mixed to certain quantities. Okay, whichever is larger. They depend on the geography, and by that I mean that depending on where you are in Canada, the snow loads will be different. You can find examples of snow loads listed for you under SB1. That's I think in Volume 2 of the Ontario Building Code, SB1 Table 2. And you'll see a list of a lot of different locations in Ontario and the various snow loads for those locations. More natural loads. Wind. Wind is another variable load which results from the action of wind on a structure. And typically, it's amplified whenever then you put the skin of that building onto the structure, right? Because it turns everything into a sail. They depend on the geography, and by that I mean where your building is located. And check out tables 1 and 2 under SB1 in the Ontario Building Code, and you'll see a list of various locations within Ontario and the wind loads associated with it. What I would also indicate is that wind is one of those few forces that has positive and negative effects. And what I mean by that, not good or bad, but simply that they can either cause pressure on a structure or suction on a structure, depending on what direction they're flowing in. Okay, next natural load are earthquake loads. These here are rare and highly variable and dynamic loads which result from ground motion during an earthquake. Okay? They too are dependent on where you are in Canada. A big portion of Canada is subject to earthquakes. In fact, I don't know if you knew this, Ottawa, Ontario is considered an earthquake zone. So whenever you build in Ottawa, you must consider earthquake loads in designing the structure of that building. And then I would add on top of that other loads. So these are loads that don't fall in the ones that I've listed here. They can include temperature loads, permanent loads, pre-stress loads, impact loads, concentrated live loads, and so on and so forth. Okay. What I would like to talk a little bit about is this image that I have on your screen. Okay. And this brings us to the concept of serviceability as well. What you see on the screen is a bouncy castle. Okay? What you see on the screen is a building, the structure of a building, and as you can tell, it's perfectly adequate in terms of strength. It's doing exactly what it's meant to be. It allows people to bounce in that structure. However, would you ever live in a structure like that? No. So this structure you see, it meets the requirements of ultimate limit states, right? Because the forces that are being applied to this structure, the loads that are being applied to this structure, are not overcoming the strength of that structure. It's resisting those loads, right? It's not popping in this case. However, if you were an occupant of this building, you would not feel safe in it, right? Pretend that this is your bedroom, and if your roommate came through your bedroom and just started walking very quickly across it, you would bounce out of your bed. It would make you feel very uncomfortable. So this here is an example where you have a structure that's perfectly safe in terms of strength, but poor in terms of serviceability, right? It's not comfortable to you. Very well. So again, the way that your textbook shows this in this very handy figure, figure 3.1, is it basically divides the load types into two types. The so-called gravity load, and they're described as gravity load because they go more or less in the same direction as gravity, which is basically down, or more precisely towards the center of the Earth. Of the loads that we just went over, we have dead load, live load, rain load, and snow load that would be considered as gravity loads, because for the most part they affect a building by causing downward forces. And then we also have lateral loads, which are not downward forces. Now, notice how I'm not calling these lateral loads of loads that go side to side. It's better if you think of them as not downward forces. And that includes wind loads, earthquake loads, and the other loads. I bring this up because I kind of want to describe to you how gravity loads are shed through a building. They start at the very top. So they're usually affecting, first of all, the load on a surface. So that typically is the roof. Again, these are for gravity loads. They first affect the load on a surface, right? Like a roof or a floor. And the forces that you have on a roof or a floor are given unit-wise, either in pounds per square foot, or PSF, or if you're using metric units, in kilonewtons per meter squared, or kilopascals. Okay? Then those forces, those loads on a surface, have to be transferred to the linear elements supporting them. So that's typically beam type structures. And those are, as shown here, then receiving those forces, because they're along the length of the beam, the forces on those beams end up being in pounds per foot, right? Not per square foot. In metric units, the units are kilonewtons per meter. Okay? So it's kilonewtons per meter length of the beam. Then the beam have to shed their loads onto the columns supporting them below. And that's what happens here. And the forces on a beam end up being in pounds or kips if it's in imperial units, or in kilonewtons if it's in metric units. Okay? I bring this up so that we can kind of understand how gravity loads are shed. And that's because when you have gravity loads applied to a structure, okay, they first start impacting the so-called superstructure. And superstructure is the structural components above grade. Okay? So by way of first going on surface elements, then shedding to beam elements, then shedding to column elements, these forces, these gravity loads, first pass down all the way through the superstructure. They then make their way to the substructure, which is what you use to describe the habitable portion of the building below grade. And finally, you pass those loads all the way down to the foundations. And that's the structural elements that are transferring all of the loads to the soil below. And while we're on the topic of foundations, I want to just give you a slight bit of information. The distinction between shallow and deep foundations. Shallow, and you see these in figures 12.2 and 12.5 of your textbook. Shallow are the kind of foundations that you typically think of when you're thinking of a Part 9 type building. Okay? But I think a better way to describe the difference between shallow and deep foundations is this. Let's start with deep. Those are the foundations you see on the right-hand side of your screen. Deep foundations are the ones that look like tree roots. That is, the footings reach very deep into the soil under the building, way past the habitable portion of that building. Okay? Basically, tree roots reaching down. You use deep foundations like the ones I show here when the soil under the building is not the best. An example of that is our very own ACE building. It has deep foundations because the soil it's sitting on is not the best. So just like a tree, it needs to reach deep, deep down underground to grip onto the soil it's on. Shallow foundations, to contrast that, don't do this deep reaching down. Okay? The bottom of the footings is the deepest part of the building. It does not need to go any further, and that's because the soil it's sitting on is relatively good. Okay? Alright, now we've talked about how gravity loads shed from the superstructure, okay, from the top of the building all the way down to the foundations. But what about lateral loads? Well, when you have a side force on a building, that building can tip over. If it's not rigid enough, right? It can tip over. So one way to do that is to add some rigidity to a building to resist these lateral loads. Buildings are great when you're using floors, beams, and columns in supporting gravity loads. Lateral loads are slightly different. So let me talk a little bit about the three ways that we'll look at how a building can resist lateral loads structurally. The first one is shear walls. Shear walls are typically the most solid type of lateral resisting structures. They're typically comprised of reinforced concrete solid walls or reinforced solid CMU walls. You can do this in wood construction as well. It's common usually in Part 9 buildings. Okay? The thing about shear walls, though, is that they're solid. So they have limited openings. Not too many windows, not too many doors through them, if at all. So typically, they're limited to, say, stair or elevator cores along the interior of a building. You only see them along the exterior of a building if you don't want any windows or doors in the exterior of a building, which typically is not good, right? Architecturally speaking. So shear walls are usually kept on the inside of a building where you don't need openings in them, and they're solid. Slightly less solid than shear walls are braced frames, like the one you see here on the screen. It's a K-braced frames. Typically, braced frames, they open up the location where you have this lateral bracing. They can be made out of steel or wood in wood construction elements. Typically steel, though, is the preferred choice. They open things up, and you can find braced frames both in the interior of a building or even along the exterior of a building, like you see here. Okay. Now the last form of lateral resisting structural elements are the rigid frames. They're the most open of these elements, right? There are no braces in any form, neither solid nor somewhat solid. They're also known as moment frames, and they can be done either in steel construction or concrete construction. Here's the thing though. They're very difficult to design and build properly. Not that it can't be done, but typically, once they're done, it's common to have to come back and retrofit that building because it's not as rigid as it was expected to be. So typically, rigid frames are kind of relegated to lower, broader, wider buildings, okay? And they're very expensive. I would recommend, if you have to use rigid frames, use them in combination with either braced frames or shear walls, okay? It's very hard to properly build rigid frames throughout the whole building, unless it's very, very small, okay? Now, that's all that I want to talk about in terms of introduction to structures. I want to thank you so much for your time, and I wish you a great day.